this is the bomb. So we're going to talk about an LRC series circuit. So we've got an L, a C, and an R. And so these are all wired up. And because these wires were so fine, I was actually able to shove the resistor right in there with it in there. So these are clearly in series. Now I'm going to connect a power supply, and you could obviously connect it like this or like that. And I'm going to explain a little bit here. Let's start with this way. This is not how I want to do it in the end, and I'm going to show you why. Okay, so keep in mind that this black is the ground of the function generator, and this red is the hot of the function generator. And that's right here if you need to see that. Sine wave, about 5,000 hertz, and I've turned up the output level. We'll figure out that in a minute. So now here's my scope. If you recall, this is ground on the scope, and this is like the hot. And the scope, if you remember, is measuring voltage. So think of this as like a DMM. You're going to touch it across, so I can measure the voltage across different elements. But now, because these two devices are plugged into the wall socket, this is ground and this is ground. If I want to measure the voltage across the resistor, I can't do this because this is ground and this is ground. This would short out these two circuit elements. Well, if I try to do it the other way, can't do it this way either because this is ground and that's. And in fact, watch, I'll just try and do it. Okay, and then when I try and measure this thing, I get a screwed up measurement. Now you might notice before I connect this, I actually do get a measurement, and that's because this versus this is a complete circuit. So you actually get a measurement until you try to hook it up correctly, and it causes this to have a ground fault. And so we have ground here and ground here. That's like the whole circuit being short-circuited. So to avoid this type of issue, I'm going to choose this other type of wiring. Not that we couldn't have got the job done that way, but I have to think more. So by setting it up like this, now what I've done is I can measure this, and hopefully we get that voltage measurement right away. I'm having a little bit of trouble, so I'm going to connect this here. And then, let's see, still having a little bit of trouble. That triggering is not quite there. So I just manually adjusted the triggering. And so if you try to do this without understanding the scope, sometimes you'll be like, oh, it's not working. But now I can see that sine wave quite clearly. All right. In addition, I want to get a second scope lead on here, a second probe. And this one, come on now. Ground has to be in the same spot. I don't need to connect it because it's already connected. These two are basically at the same ground inside this machine as is this. But I am going to put this up here like that. Can't see it very well. So I'm going to bring that down. All right, and so actually I want to switch these. I screwed up. So let me quickly switch these just because I want this to be, I have my reasons. I'm not going to tell you everything. It's the secrets of the physics universe. Come on. All right, and so now I'm going to set this up. So now this will match the way I'm going to do this in future semesters, basically, so I might use this as a training video sometime. And so I just wanted to point out that in this case, the yellow is going to be the source voltage. Look at this. The yellow is this lead. It goes from here to there. Well, that's the same thing as going from here to here. That's the voltage across the entire loop. That's the voltage across the function generator, which is the source. I can prove that to you by look at the screen. Watch this voltage, and I'm going to sweep the frequency. You'll probably see this frequency number change. And then the source voltage changes a little bit, but it's pretty negligible. All right, and let me just change like a whole decade here. So now you can see I'm at a very different frequency, and it's still right hanging in there in that 12 volt range. Let's even go further. It's auto range just to see it. So this one's a little bit long and boring. I'm sorry, it takes a second. All right, and so putting that measurement on, we're still right around 12 volts, even though now we're up to 400 kilohertz instead of 5 kilohertz. Now, in this case, we see that the voltage across the resistor is changing. Right here at 400 kilohertz, it's a very small, it's 1,000 times smaller basically. Whereas if I go back to 5 kilohertz, and then I'm just going to manually change this. Oh, there it goes. I caught it. Now notice it's up to 700 millivolts, and the source is still about the same. So what we're able to do here is we're able to measure both source voltage and resistor voltage as I change frequency. And if I could show you a couple more things, one of the tricks that you want to do here, if I wanted to get a phase angle, let me make this bigger. For getting a phase angle, generally what I do, I'll try and make these two waveforms pretty big. There we go. And line them up on the axis. I think I have to make it slightly smaller, sorry. So we line them right up on just some random line. I'll make this one bigger, line it up on the same line, and from there you could get the phase angle, but you can't see it, so now I'm going to adjust the seconds per division. And now pretty soon you can't get your measurements anymore. Oh, it's having some trouble there. But if I line this one up to a nice grid line, and this one up to another grid line, hopefully you can count the divisions very easily between this one and that one and get, so that's about a division plus maybe another 2/10 of a division. You kind of have to eyeball it. It's not perfect. It's a circuit. Let's call that good.